Good morning, students. Last time we verified the de Broglie equation by calculating the value of wavelength of electrons accelerating with v volt, and we have seen that if the volts given to electron is 100, then the wavelength is equal to the wavelength of X-rays. So if the electron is accelerating or moving with 100 volts, then its waves are similar to the X-rays. This confirm the wave characteristic of electron. This all further confirmed by the Davidson and Fermer experiments. In Davidson and Fermer experiment, the beam of electron is allowed to fall from a tungsten filament. By heating the tungsten filament, the electron beam is emitted, and it has given a V volts, and it allowed to fall on a nickel crystal. The beam is reflected in all the directions, and the intensity of a beam, to calculate the intensity of the beam in a definite direction, it is passed in a Faraday chamber which is attached with the galvanometer. So we can find out the intensity, and it's found that by increasing the volts of electron beam accelerating, the intensity of the beam also increases, and the pattern of graph between the increasing volts and intensity is similar like a wave pattern. So it confirms that when electron is moving, they have a wave characteristic. The wavelength of this beam can also be calculated by the Bragg's equation, which is 2d sine theta is equal to n lambda, where theta is the angle between the incidental rays and the and the d is the distance between the layers of the crystal lattice. It is found that the value of wavelength lambda of electron beam when it is given 100 volts is similar to the value obtained by the de Broglie equation, which is lambda is equal to under root 150 upon v volts into 10 to the power minus 8 centimeter. And it's also found that the value is similar to the X-rays of the wavelength of the X-rays when they have given the 100 volts. Thus, this experiment of Davidson and Fermer also proves the wave nature of electron. Thank you.